Okay, hello everyone, hope you can hear me. So my name is Ricardo Macedo. I'm a researcher at ASLab in Tech and a PhD student from University of Minho. And I'm here to introduce you to this webinar series on the road of HPC major challenges and new opportunities, which is a joint webinar series between the BigHPC project and the UT Austin Portugal Program. First of all, thank you very much for attending this session. Today's session, we will kick off this webinar series and we'll bring together 3 senior researchers from the Texas Advanced Computing Center for hopefully an engaging and insightful discussion about containerized application performance at Petascale. So, today's speakers, we will have Todd Evans. Todd joined TAC at 2013 as a member of the high performance computing team. He received his PhD in physics from the University of Illinois at Urbana-Champaign in 2008. He spent the following 2 years as a postdoc working in high energy physics at the University of Regensburg, and then 3 years as a postdoc in the nuclear engineering at North Carolina State University. Since joining TAC, his research is mainly focused on application performance monitoring, optimization, and analysis. Then we will also have Amit Ruela. Amit works as a research associate at the HPC group at TAC. He earned his PhD degree in computer science from IIT Delhi and performed his postdoc on the Ohio State University. His research interests are focused on feature and performance enhancements in MPI communication through novel and innovative designs. Amit has also deep interest in big data, machine learning, social computing, and information systems. Finally, we have Stephen Errol. Stephen is an engineering scientist at the Texas Advanced Computing Center in HPC Performance and Architectures Group. His research interests include performance portability, performance modeling, benchmarking, HPC metric capture. And before his current appointment, Stephen worked as an HPC system administrator and HPC support staff for 12 years and received his bachelor's in computer science at Purdue University. So I would like to inform you that you can and should interact during the 3 presentations. For that, you can use the Q&A tab to share your questions asynchronously. Okay, so during the presentations, there will be no discussions, but in the end of the webinar, we will have some minutes to discuss all questions and interact directly with you. When writing a question, please include your name and affiliation, and if you desire to ask the question yourself to interact with the speakers, you can do so. So now, let's go for the first speaker. Again, thank you very much for joining this session. And Todd, the screen is yours.
Hey, how's that look?
Yeah, it's okay. Can go, Todd.
Great. Okay. Well, thanks for the generous introduction. I'm Todd Evans, and I'm going to be describing some of the work that we've been doing in relation to the BigHPC project under the UT Austin Portugal Program, along with my colleagues Amit and Stephen. And this work is focused on looking at containerized application performance at the petascale, how to achieve that performance, and also validating that we are achieving that performance. But before I get ahead of myself, I want to just describe what high performance computing, or HPC, actually is, so that I don't know how diverse our audience is here, but I don't think that'll hurt. Describe a little bit of big data and how HPC and big data are increasingly being forced to coexist, and how big HPC is meant to address some of those challenges. And then I'm going to hand it off to Stephen, who's going to describe containers and how they actually work and their role in HPC. And then Amit will take over and describe some of the experiments and benchmarking that we've done with containers and ensuring that they're running optimally. So what is high performance computing, or HPC? The largest of these systems have hundreds to thousands of tightly interconnected servers or compute nodes. It'll often be referred to as a supercomputer. On the right, on the top there, you can see rows and rows of racks from our currently largest system, Frontera. That's about 8,300 compute nodes. And along the top there, you can see those blue lines. Those cables are kind of the magic sauce that makes these computers super. On the bottom there, you can see all those cables coming in and actually connecting into the servers. And that's what allows all these servers to act in unison and to solve some of the world's largest problems. These systems will typically have tens to thousands of researchers all simultaneously running completely distinct applications. And these applications are traditionally things like weather and climate simulations, like hurricanes or tornadoes or weather forecasting, fundamental physics like astronomy simulations or cosmology, maybe studying particle physics data out of LHC, engineering applications like maybe designing Formula One cars or rockets or studying turbulence, molecular dynamics, which is really looking at how atoms wiggle and interact in molecules. And these molecules usually are making up cells, proteins, or viruses. So for example, studying the spike protein in the coronavirus is an application of that. Material science simulations, such as designing batteries or superconductors, and also geosciences type applications like predicting earthquakes or mining, or drilling for gas or oil. So there's a whole wide, diverse variety of types of simulations that people do on these systems. So big data, which you can think of big data, it's just computing that requires a whole lot of data. It's not a purely distinct category from high performance computing. It's just a different emphasis. And traditionally, the software and hardware that supports big data is significantly different from the type that is used in traditional HPC environments. There's a couple of reasons big data and HPC are increasingly being forced to coexist. And one of them, maybe the most popularized one, is the rise of machine learning and its requirements for data. Machine learning is used on traditional HPC systems to approach old problems in new ways, maybe perhaps much more computationally efficient ways. Like it might be used to optimize the electronic structure calculations used in something like a solar cell to optimize the energy production there, or used to accelerate calculations like in the case of protein folding. And machine learning also allows us to approach new problems that we really couldn't do well before. Things like image recognition. So looking at data coming out of telescopes or MRIs, and even unique things like predicting how streets or buildings might be displaced by an earthquake. Big data is also increasingly being used through sort of more traditionally, what's considered more traditional big data methods. So things like data simulation. So when people are performing weather simulations, they might be taking in actually measured weather data, inserting that into their simulations in order to improve the accuracy of those simulations. And that can be very data intensive. Epidemiology. So again, in the case of COVID, determining how the virus spreads through a population. that requires large amounts of data coming in from very diverse sources, whether it's cell phones or hospitals, things like that. And also another example would be drug discovery, where millions of compounds are being compared to measure their efficacy against a certain infectant. So like I said, big data and HPC aren't truly different categories. They're just a different emphasis on sort of what computationally is required to solve these problems. But big data software and workloads don't fit well into HPC environments typically. HPC expects regular and predictable input-output or data movement, whereas big data really tends to have more irregular I/O patterns, like many random, frequent, small reads and writes to many different files. This can be challenging specifically to the hardware that if you tried to run that big data workload on an HPC system, the hardware that supports that is underlying the HPC system, that can be very stressful to that hardware, and it can actually make it lock up and crash. So you really need a way to control that irregular I/O. HPC systems and environments expect the software that runs on them also to be able to be customized to many different environments, or what you would call portable. Whereas big data and machine learning software is often very highly specialized and complex, non-portable. Maybe it can only be built like on one machine at Google somewhere that is very hard to replicate those conditions anywhere else. And then finally, HPC systems, they expect the workloads to share the system with other entirely distinct workloads, whereas big data workloads tend to expect that they will have exclusive access to a system. So they might expect that they will have access to required privileges that would normally be considered a security issue in an HPC system. They might expect persistent services such as databases or web servers to just always be available to them, whereas on an HPC system, that's very difficult to support. So the BigHPC project is really a management infrastructure that's composed of three challenges to try to solve, composed of three different components that try to address these challenges. Specifically, there's a monitoring backend, which tracks what workloads are running and what resources they are consuming. And what this will do is facilitate what's called a quality of service for shared resources. So it'll ensure that diverse workloads, or even workloads that are related to each other, have like a guaranteed amount of network bandwidth or memory or CPU time available to them. The next component is the storage manager, and this is going to be used to control the I/O of workloads, or the input, output, or movement of data. And again, this will provide some quality of service for that I/O. The reason that this is kind of special is the I/O systems in HPC tend to be very complex with multiple levels of hierarchy, from local memory to remote memory, local disk, remote disk, shared file systems. There's a lot of different ways that data can move through these systems and different ways that they can break. They're actually kind of fragile. And so the storage manager will facilitate stability in these storage systems in the face of big data demands. And then finally, what this talk is going to be most related to is the Virtualization Manager. And this will provide curation of software and also the placement of workloads. By placing these workloads throughout the hardware on the HPC system carefully, that allows you to enforce the quality of service for things like nodes, network, and memory. It'll also enable workloads to utilize persistent services, which, like I said, is often required by big data workloads. And finally, it'll enable the complex, rigid, big data-oriented software to run in more diverse environments and hardware, software and hardware environments in a near optimal way. This is challenging, for example, because, for example, TAC alone has more than 6 entirely different processor and network architectures that are, for the most part, incompatible with each other. They have different, these systems have different software environments. And right now, we're probably on the low end of what we usually will have in terms of hardware and software diversity. In another year, I'm sure this number will double. So this is a really challenging problem. Just a little more detail about the Virtualization Manager. It has 2 subcomponents. The Virtualization Manager Scheduler is how users will interact with the HPC infrastructure. And this is, users can request their workloads to be run through this scheduler. And then the scheduler will then take and place those containerized workloads based on input from the monitoring backend and storage manager, and try to place them in an optimal way such that they don't contend for resources or minimize their contention for resources. And then finally, the Virtual Manager Repository is what's going to enable what's known as containerization. And Stephen will talk a little bit more about what this really means. But the upshot is containers can help users to both build and run applications that are optimized for specialized hardware. So you can, and software. And so you can think that of it as it's customized for a specific HPC system. These optimized containers will be provided by the repository in an automated fashion to BigHPC users at build and runtime. Now, this is particularly difficult because containers might be used on thousands of nodes simultaneously and across, ultimately dozens of different architectures. So these tasks are not straightforward. So what the rest of this talk is going to address is some of the work that we've been doing for the BigHPC project over this past year. And that is, how do we ensure optimal container performance to our BigHPC users? How do we maintain both portability and optimal performance so that we're not wasting those very expensive HPC hardware resources? And with that, I will pass it on to my colleague, Stephen, and he'll introduce containers and their role in HPC.
Hi, I am Stephen Harrell, and I work at the Texas Advanced Computing Center, and I'm just going to talk about containers in a more general sense. Let me get to the next slide here. So the concept of containerization has a long history in computing, starting with Cherut in 1979. The primary motivation for creating container and container-like technologies has always been about changing the view that an application has into the operating system that it's running on. In many cases, it was to be more restrictive, but in our case, this enables us to run applications in computing environments that those applications were not designed for. For instance, it's common in scientific software for an application to inspect an environment that the original grad student used when they authored the first version of the software. At TAC, we may use a different operating system environment the grad student used. This causes conflicts, and we either have to spend time to resolve those conflicts, or we can bring the grad student's environment to TAC. And this makes containerization critical to BigHPC. BigHPC aims to use many different HPC machines that can come with many different environments, and containerization is a way to bring that application along with its original environment so that jobs submitted with the BigHPC project will avoid the complexity of mismatching environments of disparate HPC machines. Ooh, excuse me. In this diagram, can you see the diagram? Can I get a nod? Great. In this diagram, we can see an architecture stack for containers and virtual machines. You can see on the right the level at which a container works. It's by packaging up the app and the libraries and binaries it needs. This is especially important because all environments have libraries that can't be replaced without affecting the entire system. So this allows things that are dependent, applications that are dependent on libraries that can't be changed in the system to be changed very easily. And for BigHPC, this makes library packaging frictionless when you submit to a BigHPC. Also, just to show, virtual machines have a very similar set of features, and they were considered in our BigHPC technology stack. However, they run a second operating system, and you can see on the left there that the guest OS is packaged up along with the libraries and the application. Now, that secondary OS will have tremendous overheads, and because the HP and HPC is high performance, we can't afford the overhead of running a second operating system. There are many benefits of containerization stemming from the standardization of the compute environment. In one way or another, all of these benefits listed in the diagram are important for HPC. However, the most important features for the BigHPC project are software choice and portability. Let me define those terms quickly. Portability means an application is executable in a myriad of different environments, and software choice in this case means that an application can bring its own environment. And putting these two together, sorry, just 1 second. Putting these two together, and we have a technology that allows us to forego the complexity of building applications for each environment by providing one technology that can run in many environments without the constraints of the machine software environment. Even though there are many benefits to containerization, there are some caveats. For instance, although containers are portable among software environments, they are not portable on different hardware architectures, as Todd mentioned. For instance, if you moved an application from an x86 machine to a Power 9 system, you would need to recompile the application and any needed libraries to match those environments. The structure of the binaries and libraries will actually be different on the disk. In the container, it's no different. So if we run a container on a new architecture, we would have to create a new container with binaries that match that hardware architecture's expected binary format. And we'd have to do that for each hardware platform. Additionally, many HPC systems have specialized networking hardware and accelerators that are integral to achieving high performance in the applications. Each type of this hardware typically has its own libraries that are needed, and sometimes needs to match, and sometimes those libraries actually need to match the host system. Additionally, some devices require special support from runtime container environments like NVIDIA GPUs. This is because they have special devices within the operating system that they use to get their performance. So there has to be a connection made for the specific host in the container. This is compounded if you have to do both, if you're using specialized hardware and a non-typical hardware platform, for instance, the Longhorn cluster at TAC is Power 9, B100s, and InfiniBand. All these technologies must be accounted for in each system. And as mentioned before, the VM repository will provide containers to fit each HPC system. The primary consideration for any HPC project, including BigHPC, needs to be performance. As performance is not maintained, the value of our work is diminished. That being said, the point of this project is to reduce complexity for the user, and part of this is making applications as portable as possible. However, we still have to find out if if containers are performant, and what are the overheads, and how do we quantify that? Amit is up next to tell you about a performance analysis that we've done at TAC on multiple platforms to answer this question.
You're muted, Amit.
My screen is visible?
Yeah.
Yeah, thank you. So good afternoon, everyone. My name is Amit Ruhela, and I'm a research associate in high performance computing group at Texas Advanced Computing Center. So, so far in the first two sections, we have seen what is the big HPC project and what we are going to do within that. We have also seen, Stephen has explained about the containerization and how does it differ from the virtualization and prior technologies. Now I will touch upon the performance aspect of the containerization, and basically there are three aspects why we want to do this kind of studies before we do the actual project. The first is we want to get acquainted with multiple hardware systems which are state-of-the-art within the world, and get acquainted with how those containerization approaches works on those systems. The second requirement for these kind of studies is we want to find out what are the overheads of using containerization over the various hardware platforms, and how does the performance of containerized applications compare in terms of against the bare metal runs or native runs. The third part of this project, the aspect is that leveraging these experiences and identifying the issues or bottlenecks with containerizations, we want to better understand how to build our big HPC project so that those issues would not be there when we actually design when our system comes out in the market. So let's start with first looking at the hardware configurations. So we have carried out these containerization studies not on just some specific systems, but a variety of systems which are popular in the world. And some of these configurations are given here. The first is Intel Cascade-less system, which is pure CPU systems having almost like 8,400 nodes, having 56 processes per node. And the interconnect which we have, which is available on this machine, is the InfiniBand EDR. Apart from the CPU-based studies, we have also carried out the studies with GPU-based systems. Like we have run our containers on GPU systems. The first is IBM OpenPower plus NVIDIA V100 GPU system, which is having EDR 100 interconnect. And we have also done these studies on AMD ROM, which is purely CPU systems, and interconnect is EDR 100. Fourth one is AMD EPYC plus NVIDIA A100. So this is basically DGX2 machine. We have one machine available with us, and we were fortunate to evaluate the containerized workloads over that as well. And last one is Intel Broadwell with NVIDIA Quadro RTX 5000 GPUs. Here, as you can see, the interconnect is FDR56, which is a prior generation compared to HDR, the EDR 100 interconnect. So these are the various configurations which are like very popular, and we have tried to evaluate our containerized approaches over a variety of platforms. The next is the software setup. We have studied the three types of containerization approaches. Singularity, which is very popular in the world, like we have used it on our one of the machine, we having the version 3.5.3. Then Charlie Cloud is a Lawrence LANL containerization approach, which is basically similar to Singularity, and and we have used 0.213 version of this of this containerization technique. The third is the Podman. We have done very small scale study with the Podman. And in terms of the MPI library, we have used two flavors of MPI. One is MYP2 GDR for GPU-based workloads, and then we have Intel MPI for CPU-based systems. We have carried out our studies at two levels. One is the micro benchmarks level. So the micro benchmark level study is basically for baselining the performance of containerization approaches. And here we have used two benchmarks, like one is the Intel MPA benchmark with 2019 update 7 version. And then for the IO based studies, we have used IOR benchmark for IO workloads. Last, we have run two varieties of two kinds of scientific applications. One is the MIMD lattice computation. It's a lattice chromodynamics code, and we have run it at very large level, almost like 140,000 processes. Then the second is vector particle in cell code, which is basically for kinetic code, kinetic plasma code in physics, and then the last is NAS PTIO, which is again NAS parallel benchmarks, and PTI is one benchmark within NAS parallel benchmark. In terms of experimental setup, I would like to explain how we build our containers. We started with the base containers for Cross86 systems from the manifest file available on tech cluster on tech repository. So this is the like tech/tech CentOS -IMPA1907-1. It's the basically our containers which we have pre-built, and it contains micro benchmarks as well. Then for IBM Open Power based machines, we have used the standard container given on their website, docker:/IBM.com/Power API. So these are the base containers, and we have added our applications through overlay file systems from IBM Open Power. And for Cross86, we just modified the manifest file and added our other applications. So, and now all these experimental setup, like we have used system MPI to launch our containers. So when we launch the containers, we need some launcher, and for launcher we have used system MPI instead of the MPI available in the container. Now let's take a look at the baseline performance number. The baseline performance, we have used MPI init benchmark. It's a benchmark which just do the MPI initialization over all the processes within a given node. It doesn't call any point-to-point operation or collective operations. Only the operations which are there in MPI init in MPI is being called. So as you can see, we have run this benchmark from 3,584 processes to almost like 0.35 million processes over the 6,144 nodes. The maximum capacity of this cluster was 8,400, and we have used almost like 6,144 nodes. This benchmark shows the performance of bare metal runs, which is named as native, and then for Charlie Cloud runs. So as you can see, the performance doesn't differ a lot between the native and Charlie Cloud runs, even up to the 0.35 million processes. We do see like the containers incur almost like 50 to 60 seconds of overheads for 0.35 million processes. But in HPC systems, most of the applications runs for several hours or several days. And that 1 minute of time, 1 minute of overhead is nothing compared to their actual run. So I can say that Charlie Cloud shows almost like no significant overheads in containers initialization. I mean, it doesn't incur significant overheads. The only overheads which are there in initialization and tear down, but they are not significant. Next is after baselining the performance of containerized runs, we have evaluated collective benchmark, which is MPA BCAS. So BCAS is broadcast, and what it does is one process sends a broadcast message to all other processes within a given job. And we have run this benchmark from, in this configuration, we have used 1 ppn. 1 ppn is one process per node is launched, or one container per node is launched on all the nodes. So we have varied this run from 64 nodes to 6,144 nodes. And you can see that the performance is almost similar to what we have seen in the previous slide. But this is just the total runtime. But if you compare the actual time taken by MPA BCAS benchmark at various message size in the left figure, you can see that at both level, like whether it's a small message from 1 to 2 raised to 1 to 2 raised to 8, like 256 byte, or whether it belongs to 2 raised to 22, which is 2 MB of the message size. The performance of native and Charlie Cloud runs is almost identical. So what it means, once the containers are initialized, there are no overheads in running the application or the benchmarks from the containers or the native runs. So this experiment was conducted on Cascade Lake plus InfiniBand HDR100 interconnect. In the next evaluation, we changed the ppn, the processes per node or containers per node, from 1 to 56, which was the full ppn, maximum ppn supported on that node. And by this way, we have evaluated the number of, the performance of containerized runs from 3,000 processes to 229,000 processes, or 229,000 containers. So again, the performance trend is similar. Container runs don't show any overheads, and the performance is on par with the bare metal runs. The next is MPA all-to-all benchmark. This is just like one example to show on the DGX machine, that we have run it on DGX machines as well. And the cluster is basically AMD EPYC plus NVIDIA A100 GPUs. All-to-all is a very dense communication benchmark in which every process sends message to every other processes. So this, even with the dense communication, MPA communication, we didn't find any significant overhead with the containerized runs. Now, after baselining the performance at the micro benchmark level, we ran the applications, which are the scientific applications. The first application is MIMD, lattice computation. So in this application, we have measured the time to solve the conjugate gradient, which is on the first figure. And then we have also measured the Linux time, which is the time exposed by the Linux time command. And then third is the memory consumption. In the first figure, as you can see, there is no significant difference between containerized and bare metal runs. The only difference which we found is in the Linux time, which shows like at 140,000 processes, there is slight overheads. But these overheads are insignificant, I would say, because this run was run for only just like few minutes. In practice, MILCs run for several iterations, and we have just run one iteration. So if you run it for several hours or maybe a day, you'll not see your containers initialization or tear down overheads would not be significant compared to the entire time of running that application. Next, in the last figure, we have evaluated the memory consumption by containerized run and the bare metal runs, and we didn't see even a very minute difference between these containerized and bare metal runs. So it means they containerized approaches do not consume a lot of memory as was taught in the virtualization era, and their performance is almost on par with the bare metal runs. We have also run MILC on GPU-based systems, and in this we have run up to like, this is just one example where we have shown for the IBM OpenPower plus InfiniBand EDR100 and NVIDIA V100 GPUs. As you can see, there is no significant difference between the bare metal and containerized runs. The next application is VPIC, and this example shows the VPIC runs on GPU nodes, and we have run it on 32 to 256 containers, and then we have also run it on Intel Broadwell plus Quadro RTX 5000 GPUs. So by running containerized approaches across two clusters, and we have identified if there is any difference between if there is any performance difference or due to the architectural differences between the hardware, and we didn't see any significant overheads across the architectures, and within the architecture also we didn't see any performance overheads. The same experiments were run on CPU-based systems with AMD ROM and Intel Cascade Lake, and the trend was similar. So with this, I would like to say that containerized approaches have majorly improved the portability of applications on diverse HPC hardware. And they are also recommended because most of the developers who build the containers, they also apply the optimizations within those containers within the containers developed by them. So as far as with experimentation, I can say that containerized approaches are almost like portable, and then they have also very good performance compared to the bare metal runs. Now I would like to I would request to give a brief summary of the entire work.
Yeah, sure. So just what we've covered today, big data workloads are becoming more commonly seen in HPC systems, especially as machine learning grows in popularity and prominence, and people figure out how to utilize it. It's tricky because big data and HPC don't readily coexist. The big data, the software that tends to support big data applications is just not super compatible, not immediately compatible with HPC systems for a variety of issues that we covered. But the Big HPC project is addressing these challenges through the three different components, the monitoring backend, the storage manager, and what we focused on today, the Virtualization Manager. The Virtualization Manager provides portable and optimized containers for a wide variety of workloads to run on diverse HPC systems. We'll provide that performance and portability based on some of the methods that we described here. There's different ways that you can go about building these containers. And so what we really wanted to do on this work is validate the approach that we've taken to actually build these containers. So trying to optimize the software level portability while maintaining very low overheads due to the utilization of the container technology. And this requires a careful matching of the containers themselves to the hardware that they're running on. And finally, we've validated our approach, the performance of Big HPC's container solutions, showing that there's really no significant overheads compared to the bare metal runs. We have looked into, I don't think we discussed much in this talk, that there's no security issues arising in HPC environments, but that's a big consideration. And finally, we validated the performance using two different container technologies on HPC benchmarks, both scientific applications and micro benchmarks at, well, as far as we know, the largest scales that it's ever been studied at, up to 6,144 compute nodes. So about a third of a million processing cores. We presented this work, the preliminary work at the Supercomputing Conference last year, and most recently at the International Supercomputing Conference this year. So thank you everyone for your time, and be happy to accept any questions. I think you can advance the slide. Oh, okay.
Yeah. Thank you, Tal, Stephen, and Amit. It was a really great talk. We already have some questions here by João. I think you can ask him. You can ask the questions himself. Let me just try to unmute him. João, can you unmute yourself? No, I can ask the question. Okay, so João Paulo from Inestec is questioning, will the support for containers change the way users deploy their applications at supercomputers? If yes, do you believe this task will be made easier or more difficult for users? Also, can this change limit the adoption of this virtualization technology on HPC?
So users are already using containers on HPC systems. We have support for that. But the problem is they tend to be using them in very inefficient ways that kind of cripple their performance. So for example, a lot of times when a user will just naively employ a container on one of our HPC systems, it will use the Ethernet network, which instead of the InfiniBand network or the high-speed interconnect. And this can slow an application down by an order of magnitude easily. And so BigHPC is trying to help with that, try to ease that or mitigate that problem by providing containers and optimized applications for specific HPC systems, so that the user doesn't have to really think about it. They're on a system and they request a container and they get the optimized correct one for their needs.
Okay,
Thank you. I believe you can hear me now, right?
Yeah.
Yep.
There was a delay. Hi, Todd, Hamid, and Stephen.
Hi.
Thank you for the presentation. Very interesting talk. So I have another question, if you mind. Given the work you have conducted so far and this evaluation you showed, what challenges you think that are the most important ones that need to be solved to have containers in HPC in the way Todd was describing at the beginning of the presentation, to have a fully complete management software for users to deploy their containers and big data applications? And if possible, given these challenges, what challenges do you think need to be fixed at the container technologies that exist so far, Singularity, Charlie Cloud? So what the developers of this technology should support, what features are missing, and then what features are missing in terms of integration of these tools into the HPC software, management software and deployment software?
So, yeah, I would say that the container technologies now as they stand are finally pretty mature. The main issues that we've had in the past were security issues, because a lot of these approaches require some kind of elevated privileges at some point in the workflow. But they've worked, the people that develop this stuff have worked really hard to mitigate those issues. And so, I mean, even 2 or 3 years ago, we were very hesitant to support these technologies on our systems due to the constantly arising security issues. But they've definitely been significantly addressed, and we're very comfortable now supporting these, and in fact we do on almost all of our systems. Again, it's related to what I said in my previous answer as far as challenges go. It's not clear a lot of times. It's easy to take one of these containers and just run it on the HPC system, but it's not clear a lot of times to the user if how well it's performing, how much they've lost, how many resources or how much resources that they're actually wasting by using a container that's not optimal for a given HPC system. And then related to that, one of the main challenges, I think, with providing this type of support in BigHPC is just the wide variety and complexity of HPC hardware and software. So yes, we want to be able to provide an appropriate container for whatever system that the user plans to run on. But enumerating all of those possibilities is impossible. So the approach that we're taking is we'll support systems as HPC gets deployed on them, right? Like we'll support all the different variety of systems at TAC, which is, we do have a pretty decent variety, so that's not a bad start. And then we'll move on to Mac, and then we'll move on to whatever clients we have that come in the future. But I would say supporting that, the combinatorics of supporting all of these different architectures and softwares is one of the main challenges.
I would like to add two more challenges regarding this. So far the studies which I have conducted based on the CPU and GPU systems. So if you are available with the source code of an application, then it's very nice, like to generate a containers for that particular machine or particular hardware. But if source code is not available and you are depending on the underlying libraries available on that systems, then it's not always easy to run the containers in those environments. Working on the GPU systems, it's not right now, though Singularity provides certain options to embed the GPU libraries from the underlying systems into the containers. But Charlie Cloud, there are some issues, like it's not easy to set up those sample libraries or the libraries to add the GPU-based code within the containers. So that is one thing which containerization approaches should take care into account, like to make the job of developers or the users easier to run the GPU-based workloads over to the GPU machines. The second aspect is, like, while working on the containers, and if you want to identify the issues or if you want to debug any containers, right now what we do is like black box approach. We know what is happening outside the container, but no debugger currently supports debugging inside the container, running it from outside. So that is one thing which needs to be taken care, because outside perspectives are not sufficient to understand the performance bottleneck or to understand the various other tuning options which we can provide inside the containers. So these two things are required from the implementation perspectives, but what Todd has said are valid in general.
Okay, thank you.
Okay, so now, Mario David, do you have any questions or comments?
Good afternoon, everybody, and thanks a lot for the presentation. As you know, we are quite interested in all this, since we also have UDocker, and we'd like to see how UDocker performs in even comparing and all that. I had a comment about the users and making containers, and the point that you have made about let's say the performance that, I mean, the best people who know the performance and how to do the best thing on compiling whatever is the administrators themselves. What I see is that container technologies in principle can ease the work of the administrators because they may not worry much anymore about the underlying operating system and libraries. that means that probably they are the best ones to compile themselves the containers for the users. And if a user comes with strange requirements, which probably, as you know, happens quite a lot of the time, you will not worry as much with the underlying operating system and libraries, and you can let's say set up and configure and compile inside the container as almost as you want. So you still have, it's like, I mean, the administrator still, I mean, you compile the modules. I mean, you compile the software which you do the modules. So this is a bit of a different way of doing things. Like, I mean, you will do it in containers and probably have less hassle about what is in the underlying systems.
Yeah, and this is, I was trying to emphasize in this presentation, it's especially a big issue for the machine learning and BigHPC type applications. Like if you've ever tried to build TensorFlow from scratch, that's nearly impossible. Right?
Not me. That's why, for example, in UDocker, it's simple because I just get the Docker, the official Docker image of TensorFlow with whatever CUDA and blah blah version there is, and I manage. Fortunately, I managed to run this with UDocker without any change whatsoever to the image. But then, I mean, if you have your own Python code, you just say that, okay, this is, you have the base image, which is the official one, and you put the code inside, and basically that's it. And this is in fact one of the things that I wanted to try in TAC and other systems with GPUs, is just to experiment on this type of things. I mean, getting the official images, because as you say, I mean, TensorFlow is one thing. There are other things. I mean, I in the first UDocker paper, there were some people from CERN, from the theoretical division, doing some simulations and calculations. That, I mean, they were using libraries from CentOS 5 and Fortran 77 from very old time.
Yeah.
So it was a huge confusion, you know. And from the moment that they saw that they managed to have a container with everything that they wanted, and they managed to, in fact, run with UDocker. I don't remember if it was a TAC or, yes, I know that they were running in an American HPC system, and they didn't bother anymore because it was a big confusion to try it with these old libraries and systems and all that to do this type of thing. So yeah, and this is kind of, I mean, on the one hand, you'll have probably a lot more to pick up. I mean, it's not only, and probably you can customize and make as best performance as possible the underlying operating system and libraries without worrying as much probably as you do then with compiling certain applications and libraries which the users are asking.
Yeah, and that use case is actually I don't know how common it is, but in their case, part of the reason they use those ancient you know, out of date software is because it's been carefully validated, and they don't want to have to redo the validation, right?
Correct.
It's a time-consuming, labor-intensive thing. So it would be impossible for them to run that stuff anywhere without this container approach.
Okay, thanks, Mario. Does anyone has another question? We already probably on the time to terminate the webinar. So I'll just ask a fast question. So basically, in the previous model, jobs are executed on bare metal, right? So they have full access to the full allocation of the devices. So now with containers, you can allocate containers sharing the same resources, right? Because they simply can run so a few cores or a simple quote of the device or the memory and so on. So how does the scheduler considers all these metrics now, or how can he ensure fairness or quality of service?
I can take that. I think that the way that we see that the scheduler work is it just considers containers a normal Linux process. So the schedule would work in the same way that it always has worked. A container actually, the actual container executable runtime just sets up, it sets up a bunch of controls and then it gets out of the way and lets the application execute directly with the normal Linux kernel, which is why it's so performant. There's a few things that need to be kind of bridged, and so that's why we see the tiny overheads that we see, but most of the execution is actually very close to bare metal execution.
Okay, thanks. So I think we can end here this webinar. Let me just share my screen. Okay, probably you can see it now. So thank you very much for joining us. It was a really insightful talk from Todd, Stephen, and Amit. The next webinar will be about what is the impact and is HPC ready for big data storage? That will be on September 16th. And then see you on the next webinar. Again, thank you very much for the speakers, and thank you very much for the attendees to joining us.
Thank you.
Thanks.
Thanks. Bye-bye.
Bye, everyone.